I've had bacterial pneumonia twice, once when I was 2 and again when I was 6. When I had it the second time, I remember having to take this disgusting cherry-flavored medicine. My mother would beg and plead with me to take it. "Julia, you're very sick. If you don't take this medicine, you could die." And with all the conviction a 6-year-old could have, I said back to her, "I'd rather die." Now, my mother was right, of course. Without that medicine that I now know is antibiotics, I likely would have died. The advent of antibiotics in the early 20th century raised life expectancies worldwide by 10 to 20 years. An infected wound was no longer a death sentence. Bacterial pneumonia was survivable. Antibiotics seemed like the answer to everyone's prayers. But with overuse and misuse, bacteria started to develop ways to fight back against antibiotics. When treated improperly with antibiotics, tougher bacteria survive, giving rise to new generations that are entirely resistant to current antibiotics. Now, the best way to slow the spread of the evolution of antibiotic resistance is to simply not misuse antibiotics and not overuse them. But what can we do about bacteria that are already resistant? We can either invent new classes of antibiotics or resensitize resistant bacteria to antibiotics that already exist. For example, many common antibiotics rely on a molecular structure called a beta-lactam ring. Bacteria that are resistant to beta-lactam antibiotics can break that ring down by using an enzyme called a beta-lactamase. But we can fight back against beta-lactamases by inactivating them using special small molecules called beta-lactamase inhibitors. Now, how do we find such specialized molecules? We've all heard the phrase, "the enemy of my enemy is my friend." Well, many bacteria naturally produce molecules that are able to help them fight competitors in their environment. My research specifically focuses on a type of marine bacteria called Pseudoaltrimonis, which was only classified about 30 years ago, so it has lots of unlocked potential. Within Pseudoaltrimonis cells are factories that produce a plethora of small molecules, some of which have antibiotic potential. My goal is to isolate and test these molecules as new antibiotics or beta-lactamase inhibitors. So far, I've managed to extract all of these molecules together, but now I need to separate them and test them individually against resistant bacteria. Once I know which ones fight the bacteria, I'll isolate and purify them in a larger quantity and then analyze them to figure out their molecular structure. Bacteria can be our foes. They can cause illness and death, but they can also be our friends, giving us ways to fight our common enemies.